Hello everyone, welcome to the next lab of EC 573 Advanced Embedded Logic Design. In the previous lab, we discussed about how to create a stream compatible IP in the HLS, how to export the IP in the vivado, how to integrate the IP in the vivado block diagram, and how to test it using the SDK. In this lab, we are going to take our discussion further and we will understand how to optimize the IP which is created in the HLS to improve the performance. For that, we will start with the example of the matrix multiplication. Let's take the matrix multiplication of 3 cross 3 matrix. So we have the matrix A here, we have the matrix B here, and the output matrix is C. So we know that to perform the matrix multiplication, we'll multiply each row of the matrix with each column of the matrix B element wise, and then we accumulate the multiplier outputs to get the output C1. Then we'll stay at the row 0, first row of A. We move to the second column of B to get the output C12. Similarly, by using the third column of B, we get the C13. Then we will go to the second row and we'll repeat the process for every column of B to get the second row of C, and the same with the third row. For every column of B, we'll get the third row of C. So basically we are doing a lot of multiplication and we are doing the accumulation to get the every element of C. So we'll see that in case of the A, we'll have the 3 iteration. We'll call this iteration as a row wise iteration, this one, and this one. Then for every iteration of A, we'll have the 3 iteration of B. We'll call this as a column wise iteration. And for every iteration of A and for every iteration of B, we will see that there are number of multiplications which we can see that as a 3 multiplication and 2 addition to get the output, one output of C11. So basically we have the 3 for loop. One loop goes over the every row of A, that is the outer for loop. Then there is a inner for loop which goes over the every column of B for every row of outer loop, and then you get the third loop where you do the element wise multiplication and addition to get the output of the third one. So in this case, you can see that the loop 1 goes through the row, loop 2 goes through the column, and loop 3 goes to the element wise multiplication and accumulation, and so on. So basically matrix multiplication is the 3 for loops written together. Now we will be writing the for loop, writing this code. So to just give you how the code will look like. So for example, we will have the input A through which both the matrix A as well as B will be taken in, and then output will be available at the another stream interface. So you have this IP where you have this one stream interface where you get the A and B sequentially, and you have the output which is C. So via HLS AXI interface, which we discussed in the last lab, we make it as a stream interface. In the .h file, we'll have the structure of AXI's data, which will we can assume that initially it will be float data and the 1-bit last signal. Okay, float data and the last signal, that is the 1-bit. Then you can see that the received data I'll store in my local memory, so that because stream data I'll be receiving sequentially, I need to store it in my local memory because I want to reuse it multiple times. And then to store it in the local memory, I can use the for loop. Say for A1, I can read the data. Okay, then I'll store the data in the A, and over the same interface, I'll read the next matrix and store the data in the input B matrix. After that, I'll do the matrix multiplication. So these are my three loops, loop one, loop two, loop three. I'll do the multiplication and the accumulation to get the output results, which I'll store back in my output matrix. And then from this output matrix, I'll write the data on the output stream interface and I'll generate the appropriate last signal. This is how the code looks like. Now we will go to the HLS and understand entire design flow of the HLS. Okay, so we'll start with the new project. So make sure that when you create a new project, there is no space in the address of your project folder. Okay, so then click on next. Here we'll not mention any top function, we'll do it later. We'll not add any test bench file, we'll add it later. Here in the uncertainty, you can mention it as a 1.25 and make sure that you select the Z board if you want to test it on the hardware and you have the Z board with you. You can select any other board depending upon your hardware requirement. So now in the source file, we'll add the new source file, say matrix multiplication.cpp. Along with this one, we'll add a new file for the .h. Okay, and in the .h file, like we did for the last one, we'll first add the stdio.h file. Then for the stream interface, we'll add the HLS stream.h file. Okay, then we'll fix the matrix size. So we'll add the corresponding matrix size as a parameter. Then as we discussed in the last one, we'll add the AP in for the last signal, which we want to make it as a 1-bit signal. Okay. Then since I'm going to develop the multiple solution, I'll have the another parameter indicating which solution is active. So we'll say that the solution 1 is active, so that we'll be able to move between the different solutions. Now for the solution 1, what I'm going to do is that I'm making sure that all my variables are of the type float. Okay, so if define solution 1 type def float mat d type. So I'm making sure that I'll be using the mat d type throughout my code, so that depending upon the type of solution I want to develop, I can move around between the float, double, half float, and so on. Okay, and if okay. So this is done. Then what we need to do is that we need to define the structure like we did in the last lab. We are going to define the AXI structure. So you can see that the structure is of the type matrix data type, and the last signal is of the type unsigned integer of 1 bit. And then we need to define our function so that we don't need to redefine it in the other places. So we have this function matrix multiplication. This is the first solution where the input is A and the output is C. Okay. So this completes my .h file. Now I'll take this function. Okay. So this is my function. So in this function, first thing I need to add is my .h file, which is we have just written. So this is the .h file has been included. Then what I need to do is that I need to define the internal variable to store the uh, matrix. So what I'm going to define is the three internal variable to store, to receive the matrix and to output the matrix. So all the variables of the type float as we define in the .h file. Local input and output matrices. So this has been defined. Then I'll need indexes for the for loop, row, column, and index. These are the three variables I'll use in the for loop. And to receive the data over the stream interface, I need a local one. So I'll say that the local stream. Okay, so I'll use one for this one. Now, if you see this, now the next thing what I need to do is that I need to take the data on the stream interface and store inside my corresponding matrix. Okay, so again I use the I use the two for loop. One goes over the row and the second goes over the column. It takes the data and in on the stream interface, and it copy the structure. This structure has the last signal and the data signal. I'll take the data signal here and store in my input vector. Okay, saving the streaming data to the respective variable. So similar to this one, what I'm going to use is that I'm going to add the another one for the B. I'm going to read over the A interface because I'm using only one interface for both the matrix, and then I'm copying into the another one for the B. So this completes the input of reading the input. Now I will need to perform the matrix multiplication as discussed in the slide. It is the three loop matrix multiplication. So in the three loop matrix multiplication, you have the loop 1 for row, loop 2 for the column, then you define the intermediate variable for the accumulation operation, loop 3 for the each index, you calculate the output and you store the output in the output C matrix. And this output, I'll be sending it over the output stream interface. So you can see that this output for every row and column, I'll have the local stream. I'll take the output, put it into the data. Depending upon the index, I'll generate the last signal and I'll output this over the stream interface. After this, so I have completed my code. After this, what I need to do is that I need to define these as a stream interface. So I need to define input A. Right click on that, insert directives, the interface, select the source file so they are visible. select the AXIS and in A. Okay, that's it. So you can see that the stream interface has been added, and I can do the same for the out C. Now, in this case, I don't want to generate the any control signals like ready, done, and all those things. So again, I'll go to the function and choose the AP control none. So this will not introduce any control signal in my code. So this completes the function, and this function will be active only when my first solution has been defined. So I'll use the hash defined solution one and so this function will be active only when this solution one is defined in the .h file. Okay, so with this we have completed the function. Now we'll go to the test bench. So we'll have the matrix mul test bench .cpp. So in the test bench again, we are going to do the same thing. We are going to have the benchmark function, and we are going to have the corresponding hardware call to the function. So for that, we need to include the appropriate stdio.h file for the print function, matrix mul .h file for the hardware function, and math since I want to generate the data randomly. So that's why I'll be using. Then I'll have the int main. Okay, so then I'll have the matrix. I'll have the matrix multiplication here. Okay, so we will define the benchmark function. The other definitions are not needed because they are done in the matrix mul.h file. So void matrix mul benchmark function. And for the benchmark function, I'll define everything is of the type either float or double. So let's define is of the type double so that we get the best possible accuracy, where the input is A. This should be of the type matrix size. Input A, input B, and then you have the output C. So note that for benchmark function, there is no need of the stream interface because it will be implemented on the software. So there is no need of the stream interface. Let's define the benchmark function quickly. It is same as the our one loop inside the CPP file where we are doing the matrix multiplication. Ideally, in the industry, benchmark function is written by the different team than the one which develops the hardware IP. But for here, we will assume that since it is a simple function, we'll assume it as a similar. Also, sometimes you don't write a benchmark function, you have the golden reference input, golden reference output, and you compare those outputs with the hardware output. That is also possible. So this one is double. I need to define the row, column, and index here. So this completes my function. Now in the main function, again, I need to define my input and output type. Okay. So what I'm going to define is that I'm going to define the best possible input. So here I have the input A, B, C. I'll define of the type double to get the best possible accuracy. Okay, input A, B, and output C. Then I'll have the row and column for the for loop. And I'll have the local stream for the generating the stream data for the my hardware IP. Okay. Now the first thing is that I need to generate the input. So I'll be generating the input. I'll use the dot random function that will be there in the .h file. You can define the range of the random function. So let's say that we can define it as a between 0 to 100 and all those things you can take care. Then input A is defined, input B is defined. Now you can call the software function. Now you can call the software function and you get the output. Okay, so you can call the software function. So where you provide the input A, input B, and you get the output C, which is the benchmark output. So now you have the benchmark output ready. Now you need to convert your input A and input B into the stream interface. Okay, and you have only one stream interface, so that you need to convert it. So what we are going to do is that we are going to convert the data into the stream interface. So again, we are going to use the AXI stream write function. So we'll start with the A here. So we'll take the input A into the local stream dot data. We'll generate the appropriate last signal and then we'll pass it on the input A stream interface, which is there as in the function definition. So this is my input A1. So I took that input A matrix element by element, store into the data and wrote it on the stream interface. I'll repeat the same for the input B on the same interface. So local B and local stream. Okay, so this is what we have now created the stream interface for the corresponding IP. Now, depending upon which IP is active, has defined solution 1. Now I'll call the corresponding hardware function, that is the matrix mul. Here in A and out C, but both of them are not defined here, so I need to define them in my code. Okay, so in A, in B is not necessary. So in A and the out C. So now I have the output of the hardware is available, but it is in the stream interface. So I need to convert them into my local interface. So what I'm going to do is that I'm going to read the data from the stream interface and convert it into my matrix form. Okay, so this is my output C hardware. So this I need to define here. Okay, so now I have the data. Now what I'm going to do is that I'm going to compare the input from the benchmark function, output of the benchmark function, and I'm going to compare the output of the my hardware function. So this is the simple compare function which I'm going to use, where I'm going to compare the hardware function and the benchmark one. And if there is error, I'm going to return 1, indicating that the test bench is not successfully run. So then if it is, there is no error, my code will come here, I'll print no error and return 0, so that the HLS knows that your Verilog functionality is complete. So here it should be input A, right? Because you are using only one stream interface. Okay, that you need to be careful. Okay, so with this we have completed the code. Next thing you need to do is that you need to make sure that you tell the HLS which function you are trying to map it to the hardware in case you have the multiple functions. So you need to go to the synthesis in the top function, give the function name. Once that is done, then run the C simulation to see that your C code is functionally correct. Okay, my C code is functionally correct. There is no issue. Then I'll do the C synthesis so that I get the corresponding Verilog representation. Okay, so here I'll get the corresponding details about the latency, how much time each loop takes, execution time, number of clock cycles, and so on. So all those things, and you can see that I got the stream interface. After that, the next step is to do the CRTL co-simulation so that your Verilog code will be tested again the same test bench, and then you can export the IP. So now I have started with the CRTL co-simulation. So in the CRTL co-simulation, if you want to test your waveform or you want to see the vivado waveform, in the dump trace option, make sure that you select the all. In the pop-up window you will get, there is a dump trace, select all there so that you will be able to visualize the waveform, and click OK. And then it will take 1 or 2 minutes to complete the CRTL co-simulation. Okay, so RTL code simulation is successful and everything is working fine. And then if you want, you can either you can export your solution as an IP in the Vivado by using this export option. Okay, so make sure that in case you are not able to export, you are facing some error. This might be due to the year change in the Vivado from 2021 to 2022. It is facing some issues. So in case you are facing the similar issue, when you click on the export RTL, there is a option called as a configuration next to the IP catalog in the pop-up, and the version there you should select 1.1.0, and then you will be able to export your IP. Click OK, and the export should be successful. In addition to the export, you should be able to, you can do a lot of other things. For example, one thing you can do is that you can go to the analysis tab. Now in the analysis tab, you can watch what are the operations are done in the different clock cycle. Then you can use the debug tab. Debug tab is similar to the Vivado SDK, where you can run the code line by line and see what is happening at every step in your code, so that the debugging of your C code is easy. So this is very useful for in case you are not getting the correct functionality. Third thing you can do is that you can watch the waveform and you can see the corresponding waveform in the Vivado waveform simulator. So we'll start with this one. We'll click on Open Wave Viewer. So this open wave viewer should open the corresponding vivado for the visualizing the waveform. It will automatically open the vivado, so wait for a few seconds. So we'll get the screen like something like this. In case you are not able to see the waveform, go to the windows and click waveform here. So here you can see that you will be able to see all the timing signals. These are useful to understand how your IP works. So you can see that the input A is being passed to the IP over the stream interface. You can zoom that part and you can see that the data is passed. So corresponding ready signal and corresponding valid signal, and there is a last signal is also there. So you can see that the two last signal corresponds to two and data A and B. And after some time, you can see that you get the output on the C interface. So you can see the valid, ready, and the corresponding last signal at the end. So this is how your IP works. You can go into the detail to understand the different signals in case you are interested. Okay, so coming back to the vivado HLS, so you can go to the analysis tab. In the analysis tab, you will be able to analyze the how the different operations are divided over the multiple clock cycles. Again, a very important features in the HLS and one to understand how you can do the optimization. So you can see that the loop one, each iteration takes 2 clock cycles. Loop second loop also 2 clock cycles. Loop third, the matrix multiplication loop takes a lot of clock cycles. And if you see here, you can see that there is a loop 2 and then the loop 3, and the operations happens in the loop 3. You can see that the multiplication which takes 3 clock cycles, and the addition, floating point addition, which takes 4 clock cycles. In the 5th clock cycle, the output is available, and then you are writing the data back in the loop C. In the resource viewer, you can see which are the ports are used, memory ports, expressions like what expressions corresponds to which line of your code. You can go to the source, and in the below top you will see that which line it corresponds to. So again, a very important tool for analyzing your architecture. Here you will get which are the resources are being used in your hardware. These are the things being mentioned here. Okay, I'll leave it to you to explore the debug one. It is similar to the Vivado SDK. So with this, we have completed the first part of our lab, where we have wrote the matrix multiplication code and verified the functionality. Let's go back to our presentation. Okay, so we have completed this code. Then you can see that we got the total clock in a 10 nanosecond clock. You can see that our code is using only 7.256 nanosecond, and the clock uncertainty was 1.25. So from the 10 nanosecond, if you reduce 1.25, we had the total 8.75 nanoseconds, and our code is able to complete the operation in 7.256 nanoseconds. So we have sufficient buffer for the routing delays and the other details. Then total latency for calculating the matrix multiplication is 6148 clock cycle. Okay, so this is the total number of clock cycles needed to receive the input and to provide the output. And to understand this, we need to understand this table. For example, here you can see that in case of the loop A1 and A2, where you are receiving the A over the stream interface and storing the A in the local memory, you can see that the second loop where you are receiving the data, its iteration latency is 1. That means it takes 1 clock cycle to execute 1 iteration of that loop. Since we are matrix size is 8, there are 8 iterations, so that takes 8 clock cycle. Here you are taking the 1 clock cycle to enter the for loop and 1 clock cycle to exit the for loop. So that's why total iteration latency of the upper loop is 10 clock cycles. And since there are 8 iterations row 0 to row less than matrix size, it takes 80 clock cycles. Okay, so here trip count indicates the number of iterations. Similar the case for the B1 and similar the case for the C1. Here every iteration is 3 clock cycle because you are writing the data, reading the data from the matrix and writing it over the stream interface. So that's why it takes 3 clock cycle. Since there are 8 iterations, so it is 24. There are 8 iterations, so it takes total 24 clock cycle. 1 clock cycle to enter, 1 clock cycle to exit, so 26 clock cycle, 26 into 8 iteration of the upper for loop. That's why it is 208 clock cycle. Then this is the loop is important because it takes the most clock cycle. This is the matrix multiplication. You can see that there is a first loop which has the 8 iterations, second loop 8 iteration, third loop 8 iteration. Now the third loop where we are doing the multiplication and accumulation without any optimization, the code will do serially. So it takes 11 clock cycle for every iteration. And since there are 8 iterations, it takes 88 clock cycles. Then 1 clock cycle to enter, 1 clock cycle to exit. So it takes 90 clock cycle. 90 into 8, you get 720. 1 clock cycle to enter, 1 clock cycle to exit, you get 722. And then 722 into 8, you get 5776 clock cycle. So the two things we need to understand is we need to understand how we can improve it further. And second thing is how we can avoid the use of two loops and how we can reduce these 2 clock cycles, one for entering and one for exiting. Because if you use 2 hierarchical loops, that is the penalty. So how we can get rid of those 2 loops? That are the things we need to look into. And this is the resource utilization, which indicates that we are using 3 block RAMs, maybe 1 for A, B, and C, 5 DSP unit, I think 3 for the adder and 2 for multiplier and like this, or 3 for multiplier and 2 for adder. Then 348 plus 386 flip-flops, the total 734 flip-flops, 1428 lookup table. So overall utilization is not that much, but we should be able to reduce it further, or we should be able to increase it to reduce your latency. So that is always a trade-off between the execution time and the resource utilization. Okay, so this completes the first level of code and its analysis. In the next one, we will see that how we can speed up the code further.